Okay, let's start today's session. So we are here for the uh, last week's problem-solving session. So, uh, so, so here we'll talk about the last topics that have been discussed during this week, and is particularly on something on renormalization, and there are also some couple of related questions to it, like which is also been like given in your assignment. So yeah, we'll address them, and also we'll finally like I mean end your entire problem solving session with this. And yeah, that has been your all the different sessions that we have done like over last like 6 to 7 weeks or 7 weeks. So this is your eighth week finally, and then in couple more days, like you would be having one more session. So there we'll see try to recap a few of the important things like which we have discussed, and also if there are something crucial that we have missed out, we can also address them. And also definitely if there is anything more, any issues from your side as well, like we can clarify them. So for one last time, that would be in a few days, or I think in 2 3 days we would be having that session. And yeah, but for today, we'll look into renormalization group. So, like, what is it, and probably you have seen this in your lectures already. So, we'll try to like just briefly recap, and then we'll try to see the assignment questions, so, like, which are couple of them are there. So it's not like a objective based question. Rather, you have to like explain sort of things, and then you have to like derive things there. So yeah, we will be discussing that. And okay, so renormalization group. um, so particularly we will keep our discussion like and also in your case as well, like if you see in the lectures, the most of this discussions on this context has been restricted to the Ising model. So Ising model, like we have seen it, we discussed it in one of the previous problem solving sessions. So we have covered some of the methods, or the like like you would have like seen the transfer matrix method, and other ways to find out like how the thermodynamic properties of Ising model like can be calculated. And yeah, so we have calculated them right from the partisan function, and what are the different methods to do that. So yeah, so you have seen that in maybe in previous to previous week. So in that week only, it was also introduced in your lectures. So yeah, so and hopefully you have gone through all of the lectures. If not, like there are a few more tests left before your test. So also try to go through them, and and also don't forget to miss out the assignments. So yeah, those would be at least something very essential for your test to yeah. So you can understand like the questions would be more or less would be on that relevant terms which you have seen in your assignments. uh, okay, so renormalization group. So basically like so you have seen you have we have discussed various statistical systems so far in your course. Like you have seen like, a lot of statistical mechanical problems. Now, why do we need this renormalization group? So So basically, how could you say, like, how could you define this renormalization method or renormalization group, what we are calling here? So, mm, see, the renormalization group is a method that studies how the parameters of a physical system change under scale transformations, uh, and also it allows determining the fixed point. So allowing the determination of fixed points, uh, then critical exponents as well, critical exponents, and universal behavior near behavior near phase transitions. So that's a bit uh, long definition to start with. So we'll try to go like bit by bit. So what is this method is basically, so when you are talking about statistical systems, so they have very like a very huge degree of, like, they have very statistical systems are uh, uh, statistical systems have large degrees of freedom. So so technically, when you have a very, when you have to deal with large number of like the individual microstates of the system, or when you have to deal with the individual entity of your given system, like, it becomes really I mean, uh, it becomes really I mean, challenging to like account for various properties, and we have seen through certain uh, statistical prescriptions, like defining partisan function and then from there deducing all the thermodynamic properties, has been helpful. But then still there are questions that like I mean, up to what scale we can do this, or is it like going to remain same if we uh, do with even more larger and larger degrees of freedom. So here the idea here is to see that, suppose if even if you have been given with some Ising model, so it's a very large infinite Ising model system. So what happens, like, if you start uh, breaking that Ising model into small subgroups, like the Ising model, like it itself has many spins. Like, I'm talking about the simple Ising model system, a one-dimensional Ising model system. So, like, it just like keeps going like this, like on and on forever. So, so what happens if I do not see the system from a very microscopic scale, meaning I don't see individual spins of the system. Instead, I only look in a some larger scale where I see only a few of them. I see some some spins I can see consider two spins or three spins at once and keep going, and I skip them in betweens. So that is like I am scaling the system. So and in that way, like what would I get? Will I get the same thing back again, like same thermodynamic properties, same features of the system. So that is what renormalization group does. So renormalization group in that method, so you basically you scale up your system such that like you do not have to microscopically deal with individual spins. Rather, you group them into some like in some way where each group will behave like your single entity right now. So let's say here you had three spins. So now you are grouping three spins, let's say, into something like single spin, and then you keep doing this, and then whatever the result of this new spin then you will have. So will this going to remain same? So then this renovation group tells that like it will going to be the same. So that is what the benefit of uh, like understanding this denomination group, because it helps you understanding physics at different scales, and helps you to understand how basically the parameters of your system will scale when you go from different uh, size of your system. So from a microscopic size to macroscopic size, or even more larger than that. So when you go at different hierarchy, when you like go bottom to down, or bottom to up, bottom to the top, or also top to the bottom, so you can understand how the parameters or the couplings of the system like basically scales. So that is one important thing that we will be looking at, and what we'll try to see the problems as well. And then there are other things as we were also discuss. We'll discuss how it also helps in determining these fixed points and critical expoints, and uh, yeah. So we will see them. Maybe we can start with understanding the prescription of renormalization group. Uh, so okay, maybe we can see the question which was there in your assignment. Something we start. So there was first question. So explain the block spin uh, procedure in case of the IV model. So right. Uh, so what you basically do in this block spin procedure. So this is what. we just what we discussed about what is renormalization method. So basically the idea here is the block spin. This is also known as let's something garden of prescription or garden of construction. So garden of construction, the one who came up with this idea. So this procedure is a real space renormalization method. So it's a real space renormalization method, meaning in the same as you define your Ising system, Ising model in the real space, in the basically in your position configuration setup, you can you can apply the renormalization method in that real space configuration itself, and from there you can see how your system will scale up or scale down. So and or otherwise, like there are other renormalization schemes which are done in the momentum space. So where you have to first take the Fourier transform of your Ising Hamilton. You have to write down the Hamilton in the momentum space variables, and then you apply the renormalization scheme. But in this block spin procedure, we do only at the real space. So so this is a real space renormalization method. Where, so that uh, coarse grain that basically you cross yeah, you basically coarse grain the system by this means you basically uh, first you divide uh, your divide the lattice into small group into small blocks. Then second, you integrate or integrate out or partial summation. Or basically this means take an average of all spins in each block and represent them uh, by a single one. So the result is a new lattice with new spins and new lattice spacings. So like how could you like able to picture this? So suppose let's say we are taking let's like finish this. There is one more step here. So which you like the final thing is to rescale uh, res, uh, rescale the lattice to appear as the original. So so here you basically restore original scale by reducing all dimensions. So it's like if the new lattice spacing uh, is b times larger than the original lattice spacing, the original lattice can be restored by uh, reducing the length by reducing the length scale by a factor of b. So you basically you divide it by a factor of b. So yeah, so that's quite a lot of description to start with. So that is basically in a nutshell, you have three steps to go through. So first, like suppose if you have a Ising model, let's say let's consider a 1D Ising model. Uh, a linear spin chain, a linear chain of Ising spin separated by a lattice spacing A. So, so let's say you have a spin like in this following way. Your spin, uh, so yeah, so you have this kind of like Ising 1D Ising spin system. So, so which stretches from one end to the other end, like they are infinitely extended. So, so the first thing is to group them into. So the first step was as we wrote down here. So that is about coarse graining the system. So it's like grouping them into some blocks. So so first we can, let's say we can group them into a pair of blocks like in this following. Uh, so first we can group these two out and then this, and So yeah, so and you can keep doing this, and also you notice that the separation between them is A. So now the new spin that you spin chain that you will end up. So it's like, so after grouping them, you have to take an average of all the spins in each block and represent them by that average value or the single one. So it's like you have to do trace out the you have to trace out some of the spins of your system, and after tracing out or integrating them out, you will denote them with the red with some effective spins. So let's say, uh, like this. Now you can, after this, uh, your scale. Okay, so, and now right here, so this is what you get. So from each block you have this contributions. So for this block you have this, for this block you have this, and for this you have this, and so on. So you have read, so it's basically you have scaled your system in such a way that your now lattice spacing of your system becomes twice two-way. So these are now they are separated by two-way lattice spacing spacings, and then you get a new effective spin chain system or Eigen spin. So so basically you you basically took a trace of uh, each trace of each each block of two spins, and they are placed at the centers of respective blocks. So the new spin chain system has lattice spacing. They have lattice spacing of 2A. So yeah, then the final step, like you reduce the scale back again, reduce the length scale by a factor of b equal to 2. So if you remember, we have written, so you have to scale by a factor of b. So here b equal to 2 in our case, because yeah, as we have grouped them in pairs, so our block contains, each block contains a pair of spins. So it's like we have like turned a lattice spacing equal to a system to a lattice spacing equal to 2a system. So it's like we have uh, enlarged our system into something twice. So now we are scaling it down to by a factor of 2. Then yeah, then so now effectively my system would look like something this. They uh, so it will go uh, to either ends to infinite. So now this has become a. So right. So yeah. So this is how the idea is. Like you can also try seeing this. Like if you have a something, let's say 2D Ising model on a square lattice. So you would have also seen the same thing happening. So let's say you have a 2D Ising model like the following way. Uh, so let's say this is some random spin 2D spin chain, and they are distributed in this way. Uh, so now the first task is to like do the uh, uh, this blockchain. You have to apply this creating this blocks. So now let's say this goes on every yeah. So it's a very infinitely system. So infinitely extended system. So then we start with our first attempt. So our first step is used to making these blocks. So here you can make this kind of blocks, and then the second task is to like you have to uh, take the trace trace over each block, and then you place them at the centers of this each block. The the new value of the spin, so that will be the after taking the average, um, after tracing out the average. So now and also remember the spacings here also, like they are let's say even here the spacings are of a. This is square lattice. Now uh, so the new spin that you end up right here is this. And now your spacings become twice 2a. And again, the third step here is to like turning them into sort of original form. So that is by scaling it down by factor of 2 again here also same. So the scale by a factor b equal to 2. So it's not necessarily b equal to 2 always, like it can be something else as well depending upon how you create these blocks. So again here, so this is basically your block spin process. So uh, so this is like if you see let's say if you're uh, what is basically happening here is so it's like you I think you can already see this like what we are trying to make here is like we are scaling the system into like various ways you are basically starting with uh, uh, you're basically starting with some approach where you are basically making the groups of your microscopic elements or your microscopic entities which are your spins. So you are grouping into some blocks, and each block can can be it's basically your blocks are identical in sizes that you see, and then within each block you see that like there are spins, like they can be oriented identically, and not necessarily also they will be same always. I mean, they won't be same at every time. They can be different. So even here you can see the first two blocks. If you see the spin alignments, they are not different. So, I mean, they are different. So they are not same here. But if you see, like for example, let's say, I mean, here I think all of them are distinct, but if you see the one which we started with some uh, the 2D spin, you see this block and this blocks were identical, but this is not here identical. So identical in the sense the blocking that you have done by considering the pair of spins. So in one case is in one case you would see that like they would be aligned in the same way as its neighboring one. In other case, like it won't be necessarily same alignment, like how we see here, all the four blocks are different alignment. So, but still, the statistical properties that you will find out at the end are going to give a like nice result, which always at every different scales. If you properly like if you properly uh, take care of the scaling parameters. So if you do that, like we will see with an example, basically of Ising model itself. So here and the idea here is to represent by each block by with some effective spin, like here. So we are replacing this entire thing with this spin. So and that happens after taking the average, or like you basically trace out the spins here. So it's basically if you see uh, uh, like there are three spins oriented up, and one of them is down. So it's like you are giving more weight to the up spin. So that is like how like treating out averages work. So this is how you denote the upspin for the first block, and likewise you do this. And then finally you reduce the scale to come back to the actual size of your system. So now basically what you did at the end, so you are retaining the original size of your system, that is your A. So you're retaining the original size of your system, that is your A, but you are like basically you are removing out fluctuations from the system. So you can see like when you have lot of more degrees of freedom, it basically gives you more fluctuation in your outcomes. So you are removing all this. So you have reduced your number of degrees of freedom. So into this here. So suppose if you see consider only this amount of area of your spin system, you see I mean each block has four, which means total of 16 spins. Now they have been brought down to four effective spins, and and the size is again something similar to the like your original size of your system when that spacing was 8. So yeah, uh, so maybe you can see an example. So or uh, yeah, so before, like as I was telling, like we need to take care of the scaling of the couplings carefully, and once that is done, then we'll see how the properties, the thermodynamic properties, like remain same in going from one large scale to a microscopic scale. So uh, let's say so if you start with this Ising Hamiltonian, uh, minus k. So if you remember, we have seen this Ising Hamiltonian in our one of our past discussion. So so this is the same Hamiltonian which we are writing down here. But now let's say we're putting one more constant here. This some additional constant, and this k was basically our uh, the scaling constants, and your h is your magnetic field. Yeah. So and likewise, if you remember, like we wrote down the partition function for this Hamiltonian, like, and here this SI basically takes values of plus and minus one, and you write down the partition function, which was something like given as something sum over SI over all the spin variables, and, and then exponential to this minus beta h. And so this is what you have to start with for your given spin system, and then you have to divide the lattice. Let's say you can start by dividing the lattice in. You can group all the odd spins. Let's say uh, you can group uh, all the odd and even spins separately. So, like meaning the odd spins will basically be S1, S3, S5, and so on. You group them as one, and the other is something S2, S4, S6. Uh, then what you can do, like so then your partition function will so then you can uh, sum over every second spin. So your partition function will basically become something S1, S3, S5, and this is S, and it will go on S2, S4, S6. So after summation, after summation, you get a new Hamiltonian, uh, which so this is only for only for remaining spins. So this Hamiltonian discards all the spins which have been summed over. And in this way, so you get uh, renormalized parameters. So with this renormalization parameters, you define your new Hamiltonian. So uh, and also you have to also rescale your system so that you have to get back to the original size of your system. So that is the final step which you do. Uh, so like you had n uh, so n prime is your n by 2. So originally you had n number of spins which you have reduced it by half, and then uh, your lattice spacing is now 2a. uh, so yeah, so that is what you basically you are taking your original couplings to something k prime h prime. So this is what your RG transformation does. And this process can be repeated, and you can get a different you end up with more and more new scales, and you get more new constants like k double prime, h double prime, and so you keep on doing this this making of block of spins more and more, and you can get a even more like a larger RG transformations when you repeat the same thing more and more. So this like something you can understand. Let's say um, suppose uh, or maybe like I can share a schematic image here. Okay, if you just give me a moment, I can uh, show you. Okay, I was talking about this. Mm, yeah. So yeah. So first you had this uh, you had this spin system. This is your 1D. You can think of this as your 1D spin chain. So at each circles you see some spins are oriented, uh, and you can see it's a very large spin. And for each of the spin system, the um, I mean your couplings has this value, your K. So your K is your it's K all over the system. So that is your coupling of your system, and with this K, you have a but some given X. And now, after applying the renormalization, that is, um, let's say, uh, you apply renormalization transformation, that is uh, RB. So also one thing is, so we are calling it as renormalization group rather just simply renormalization, because I mean the in the term that you see renormalization group. So initially the idea came from uh, uh, like it's a sort of mathematical property, like you deal in group theory. So it was thought of like a group, because you do some similar sort of transformations and you get a new end up with some you end up with some sort of similar group transformations. But the thing here, it was like it was not exactly group. It is something now regarded subgroups rather as a group that we define in terms of mathematical definitions, because it's not invertible. Once you go to the final renormalized group of a system, once you get the final, um, after applying the renormalization group method, the final state of the system that you get, where you have some lesser number of spins, where you end up with lesser number of degrees of freedom, but with the original size of the system, you you cannot able to like that is not, you are in taking, you're going back to your original system fully, so it's not invertible. So but in group transformations, or in actual definitions of mathematical groups, you have this invertible nature, but that property is not there. So but it has, somehow it has stuck here. The word group has been associated with renormalization, and since then this is known as renormalization group. So this is not invertible. So remember, and yeah, so this, you do one renormalization transformation, you get a new spin chain system right here, where you see it has been, it is the process of making blocks, and here you get new constants, that is k prime or k1, that denotes the new coupling constants. After first RG transformation, and then uh, you if you do another renormalization transformation, so you get another so it's like again you are rescaling, again you are applying the block method, you are creating this different subgroups once again. So it's like uh, further reducing the degrees of freedom, and here you have new uh, constants once again, and also if you see, you can get, you can also, you could have also done this instead of going to the same. So you could have started from here, and could have gone directly to here. So you could have started from here, could have directly gone here. So this would be RB square. So it's like, or let's say, I can say that this is something like RB R tilde prime, or yeah, R tilde B. So this is your transformation. So your R tilde B is basically RB times RB is uh, it is RB square, or better, this is something. Yeah, that is fine. So that is how, like so this is also a property of renormalization. Yeah, and and this entire thing, like if you see, when you keep doing this uh, denomination method, when you keep applying this, so you can end up with this following final system. So, and this is basically known as your, or basically you are doing RGB. You are, so otherwise this is also known as renormalization group flow. So you repeat the renormalization group methods over and over to your latest system. So and you get some final system, and then again you try and find out the properties and see how this matches with your original system. Yeah. So now, so this is something we have discussed enough. Like we can go to the uh, yeah. So we can go to the calculation part, which was so like it was something given like uh, yeah. So it was like explain how to derive the RG equation for a 1D Ising model. Okay, so we can start with the same Hamiltonian which we were discussing. So the one de-icing model for the one de-icing model, we have this Hamiltonian. So like we have seen this again as I was telling before in one of our previous discussion. Like we have dealt with this Hamiltonian carefully, and also like it was given quite well. I mean, it's already, uh, uh, I mean, it's very much properly explained and given in much details in your lectures. So you can go back to the originalizing model discussion slides or your discussion videos, of which is there in your portal. So uh, yeah, so the Hamiltonian is like so suppose if you have n number of your spins and like some very large number. So and these are your spin variables, the neighboring spins, and this is your external field minus c. So c is some extra constant here, extra term. So to keep it general, and so this k is just as we wrote down before, the same thing. So the partition function will be following. Exponential beta h. So and so like notational wise, like last time what we used and probably what I have written now could slightly change a little, but it will not make that difference. I mean, it would be eventually the same thing, but written down in different notations. So I can probably see that. Okay, so last time we were using this H and this big H for the okay. Um, yeah, I think more or less it's the same thing. If you uh, without, if you see the Hamiltonian without beta this time, so it can be reduced to the small h and this k, uh, uh, or probably maybe not exactly because even here we are denoting. Okay, I think it can be. Yeah, yeah. So if you see without this beta factor, like we will have this h and this j, but with beta factor you will have this small h and this k, which we have now. So that is how like we also see. Yeah. So if you have beta h, then you will have k and h, the small h. So if you take this, uh, if you take this beta factor out, so you will have j uh, and probably this another h which we were defining last time as big H. So, or otherwise, like you can think of this as last time with what we defined as this curly H. Yeah, so that is the some notational, to have that notational consistency. You can like try to write things in the same exact way, or otherwise, like these are not much relevant here. Yeah. So now this you can also write it as so, and this summation like what it was denoting. So this way of denoting the summation means you take the sum over each individual spin values. So first you can start with your first spin, then your second spin. So you sum there all the values of for a given spin, and this goes on to the last nth spin of your system, and for your, yeah. So now this partition function further, like what you can write here. So now if you see this partition function depends on n, your total number of your spins of the system, k and h. So so you can write down this si as beta h, or uh, this is k times SIS I plus 1 plus h over 2 SI plus SI plus 1. So you can write this way. So uh, so how it is possible if you see, uh, let's take this C, let's not conspiracy, but for general you can keep it. So to let you know how that you can write it, like you see our last time's discussion, a similar way we wrote down right here. So if you see, that for I equal to 1, you will have this in this exponential. So this is your, in Hamiltonian you have this two terms. So for I equal to 1 you will have hs1, and then from here you have k times s1 s2. So then for I equal to 2 you will have hs2, and from here you have ks2 s3. And then if you group bring them these two things together, you can if you bring the terms of I equal to 1 and I equal to 2 together, you can write it in this way: h by 2 uh, uh, s1 plus s2, then k times s1 s2, and then multiplied by, then you can group I equal to 2 and I equal to 3 term, three corresponding terms, and then you can group this further. So and yeah, and this can be carried over. So you can probably, maybe I can, for reference I can use this. So this is something that we discussed last week. Okay. And then further, but here, like as we discussed just previously, we are interested in uh, like grouping them. So our first task is to group them into blocks, and to group them we will first separate out odd and even spins. So group all and odd and even spins separately. So then we'll take the average to get the effective value of the block, the effective spin of the block. So for that, like what you can do, uh, yeah, you can write the following way. You can write it in this manner. So you have exponential k s1 s2 plus s2 s3. Then you can write it as hs2 plus h by 2 s1 plus s2. So basically it will be h s1 and s2. It's mistaken here, so this will be h s3. Okay, then further you can write it second exponential in the following way. So it will be uh, k s s3 s4 plus s4 and s3 plus hs4 plus h over 2 s3 plus s5. Yeah, and this goes on like there will be more such terms. Like if you see like here, I'm trying to successfully s3 or like again there is an s4 s5. So what I'm doing, like, so here is I have these terms. So if you now again further you bring this together, this exponential and this exponential. So like you get something. If you write the total exponential, so it should be something exponential h by 2 s1 plus s2 plus s2 plus s3. So it is like x1 plus x2 plus x2 plus s3. Then further you have plus k s1 s2 sorry, yeah, s1 s2 plus s2 s3. And yeah, and this gives you what basically h uh, k s1 s2 plus s2 s3 uh, plus HS2 plus H by 2 S1 plus S2. So now what happens if you do this way? Now, if I remove, if you see this particular factor here, that is what written right here as well. So if you see, if you can able to get rid of this h2 from this first exponential vector, you end up with only s1 and s3 in its argument, which means you are only making a configuration of odd strings, that is s1, s3, and also if you see the neighboring one, here also if you get rid of s4, you end up with only S3, S5, and yeah, it will carry on like further, like S5, S7, then S7, S9. So, so that is the way to deal here. That is what we can able to create these blocks. Uh, so, what essentially we are doing, we divide the lattice into sub lattices. Let's say we are dividing it. You denote the sub lattices with just open circle, or yeah, with a hollow circle, with just notation as 1, 3, 5, and so on. And this means your even sides. So so you divide into these sub lattices, and let's say if you denote the now denote the uh, so denote this bold circle sublattice, means denote this 246 sublattice system by sigma. Let's say sigma means 246, means sigma 2, sigma 4, and so on. So in that case, you can write down the partition function, where you will separating out sigmas, the even part, and the odd ones. So this will give exponential k h1 sigma 2 plus sigma 2 s3 plus h sigma 2 plus h over 2 s1 plus s3. Yeah, then likewise you have the other subsequent exponential in the following way. So this will be k times s3 sigma 4 plus sigma 4 s5, then h sigma, this will be hs4, or yeah, this will be h sigma 4. Is all the event we are denoting by sigmas, and h over 2 s2 plus sorry, this will be s3 plus s5. this will be two the next one. Yeah, and then you have more exponential factors. So now, like to get the effective, like new spin chain system, we have to sum over all the, let's say, for this uh, even spins, the sigma spins, then we'll get a sublattice system. So which means we will end up with only odd spins. So we have summed up all the even spins of the system, and then we will only get with then we will only remain with only odd spins. So that is now like we have applied our block. Uh, we have applied our process of making these blocks, and after making this block, so we end up with only odd spins residing at odd sides of the lattice system, and yeah. So for that, the partition function now, which you will have, will be the one after taking the trace over sigma, after taking this summation of sigma. So you can say that, uh, so take the partial trace over all sigma spins. So you get this sublattice partition function, sublattice partition function, that is, yeah. So then, if you take the trace of here, so let's say, uh, so you take first sigma 2, so that means you sum sigma 1, that is plus or equals to 1, uh, s. So, so it won't be sigma 1, it will be sigma 2, sigma 4. So this will be, first you have to take sum of sigma 2, then um, so you have the whole thing here, then you have to take the trace of sigma 4. uh, you can keep this part outside. The sigma 4 also you have to take the summation, uh, then yeah, then this will carry forward. So if you take the summation of sigma 2 first, which is plus and minus, then put first plus here, it will be S1 plus S3, and this will be simply H, and this will be, yeah, as it is. And then you put minus also, then it will be uh, negative of S1 plus S3, and this will be minus H. So, so this will overall give you, um, so if you do that, like you will end up with this in the following exponential forms, that is first k plus h by 2 times s1 plus s3 plus h, which you get when you put sigma 2 equals to 1, and right, and then you get another term that is exponential due to sigma t equals to minus 1. That will be again something like this time it will be minus k plus h by 2 s1 plus s3 minus h. So yeah, so this is what you will get when you put sigma 2 equals to plus 1. So this corresponds to sigma 2 equal to plus 1. This corresponds to sigma 2 equal to minus 1. And likewise, you have the other terms. So okay, so this is just for notation to understand the each terms. So yeah, then the other term you will get after applying what is sigma 4 using the sigma 4 values, that is plus 1 and minus 1 again. So you have exponential k plus likewise the same type of terms you will also get here, k plus h by 2, but this time it will be s3 plus h5, then plus h as usual, and then again exponential of k minus k plus h by 2, s3 plus h5, then minus h, yeah, and then more terms are further multiplied. So this multiplied, yeah. So yeah, so so and also remember, somehow we have to like our goal is to show that this partition function again retains this form, that is k prime s I, and this time it will be I plus 2 because we have um, like summed over all the uh, uh, even ones, so it will be I plus 2. So there is no in between spin anymore in this newly constructed spin chain. So, so this will be again Si plus Si plus 2. So and then this constant, that is plus 2z. So we'll get some constant. So our goal is to get something of this form. So this is going to be our target, because you should remember that, like this partition function is something follows that that our Hamiltonian Hamiltonian must keep its structure. So as we were like emphasizing just moments ago, that when we are doing this RG flow, so we go to new prime, k double prime, or whatever is we see here, k1, k2, k3. So this will give us to new Hamiltonian, but that will keep the form of the new Hamiltonian, just like as it was in the first place. That is the the I mean the usual form of Ising Hamiltonian. This so that is what our target here is. So accordingly, we will find how this transformation gives rise to the new coupling parameters, so such that it will take the Hamiltonian in the usual original form, and then we can write the partisan function in the again in the usual way. So now, if you compare uh, this partisan function and the partisan function that which we have written here. So to compare these two, so we have so upon comparison uh, or upon equating the two partisans, upon equating, so we have one side we have exponential k plus h over 2 uh, si plus si plus 2 plus h. Then we have plus exponential k plus, or this is minus k plus h over 2 si plus si plus 2 minus h, and this is equal to exponential of k prime si plus 2, then plus h prime over 2 si plus si plus 2 and plus 2. So yeah, so this is what like the partition function that which we found out here finally after tracing out the spins of the each individual blocks. So our block initially contained pair of spins like S1, S2, S3, S4, and from which we traced out all the even ones like sigma 2 here. After tracing out sigma 2, you get these two terms, and likewise after tracing out sigma 4, you get these two terms, and then like it will go on like there will be sigma 6 term which you will trace out, and you will get another uh, two terms, and each of this factor now becomes your new effective partisan function, and this partisan function should match with this form of partisan function, because our goal is to make our Hamiltonian like preserves its structure. It should remain invariant. Uh, a structure should be invariant upon some scale transformation. That is our goal here. So yeah, so from there like this partisan function which we found out after tracing out each individual blocks, we have if you write down properly that partisan function, uh, you will get this one. So yeah, so here like I have expanded out S1, S3, like S1, S3, S2, S1, S3 here. Here S3, S5, here S3, S5. Likewise, you will get pairs of S5, S7, so odd pairs. So for that odd pairs, you can directly, concisely write down your partisan function. Directly is S1, SI, and SI plus 2, SI, SI plus 2 in both these type of common terms. So that basically becomes effectively your the uh, new partition function after tracing out. So then upon comparing this, you can get the relation of your new couplings in terms of your old coupling. So then uh, so let's say if you put for Si equals to 1 and Si plus 2 equals to 1, then what you are supposed to get here, you will get exponential of Si equals to 1, Si plus 2 equals to 1, then that means Si plus 2 is 2, so that is 2k plus h. Uh, yeah, because this will be, no, it will be 2k plus 2h. Then you have exponential of, uh, uh, again, you have a factor of 2 here, so that is minus 2k, and then h minus h is 0, so it will be minus 2k. And so on the right hand side you have k prime plus h prime, then plus twice of me. Then same way to do for like si equals to minus 1 and si plus 2 equals to minus 1. You have the following. So these are basically we are getting some recursion relations. So uh, we'll see. So if you put minus 1 and minus 1, so you'll have minus, so 2k minus 2h, then exponential of minus 2k equals to exponential of, again on the right hand side you will get k prime minus h prime, then plus 2g again. So and then again the final case you can have here, that is also degenerate with. So once you can have si equals to plus 1 and si plus 2 equals to minus 1, or the other way around. So that is si equals to minus 1 and si plus 2 equals to plus 1. So this will give you uh, exponential of h plus exponential of minus h equals to exponential of minus k prime plus 2z. Yeah. So using this, like you can get what, like so using this relation, you get yeah. So using this, you can you can get RG recursion relation, which are basically the RG solutions of this Ising model of uh, the I mean the uh, block process that we have went through. So that is the solution that which we are ending up here, which are basically the recursion relations. We get RG uh, recursion relations, solve RG solutions, and determine and we can determine the fixed points. Uh, Right. So, how can you get this recursion relations here? Um, so, first you can do like you have to find out what is k prime in terms of uh, the old k, and also h. It can be also in form of h and g. So we need first k prime. So we have to find out, isolate what is k prime. So for that you can see, if you multiply this and this equation, and then if you multiply this and this equation, and then you divide it with this, basically what you can do. So suppose if I call this as A, B and C, so you multiply A times B, then you uh, divide it by taking the square of C. So then you get what is K. So it is like, so it is like uh, exponential 2k plus 2h, exponential 2k plus 2h, then minus 2k, then 2k minus 2h plus exponential minus 2k, then divide by exponential of h, exponential minus h square. This will give you, on the right hand side, you basically have exponential of um, k prime plus k prime, then uh, it will be minus of 2k prime, uh, minus of minus 2k prime, and all of the other uh, parameters inside the argument will cancel out. So you get this exponential of 4k prime equals to, so you can write it in terms of hyperbolic functions, which are like cos hyperbolic 2k plus 2, 2k plus h, and cos of 2k minus h. After taking the product, you get this in the numerator, and the denominator is quite straightforward. That is cos square h, and then and likewise you can also find out what will be. So you found out what will be k prime in terms of k and h. Now you can find out what will be in terms of what would be h prime in terms of all Hamiltonian parameters. So 2h prime, likewise you can calculate um, by applying the same trick. Now this time, instead of taking multiplication of AB, you can do A divided by B, and then again divided by C square. Right? Uh, or not, maybe not C square. It will be uh, it will be simply A divided by B. That will just do. So if you do a divided by b, so you get following recursion or this exponential of 2h prime, that is exponential of 2k plus 2h, exponential of 2k plus 2h plus exponential of minus 2k, then divided by exponential of 2k minus 2h, I guess, plus exponential of minus 2k. Now suppose if I take exponential of 2h overall common factor, then this will give me this following thing. Exponential of 2h, and this will be in terms of hyperbolic function cos hyperbolic 2k plus h and cos hyperbolic 2k minus h. And same way, like you can also find out what will be exponential of like the other thing which has been left out is the g the additional constant which we have. This will be g. So if you um, so if you multiply a, b, and c, so from there perhaps you get exponential of 8g. That is like you can check it. It can be written down in terms of this hyperbolic form. 16 cos hyperbolic cos square cos hyperbolic square 2k plus h, then cos hyperbolic square 2k minus h. So this just comes right if you just take the product of the relations that we showed after the after comparing both sides. So yeah. So now you finally have the recursion relations. So which are basically k prime 1 over 4 ln cos hyperbolic 2k plus h cos hyperbolic 2k minus h over cos hyperbolic square h. Yeah. And then you have h prime, which is h plus 1 over 2 ln cos hyperbolic 2k plus h, then cos hyperbolic 2k minus h. Then you have g, that is 1/8 of logarithm 16 cos hyperbolic square 2k plus h cos hyperbolic square 2k minus h, then cos hyperbolic square h. Yeah. So yeah, right. This is what you finally end up with this solution. So uh, so now in this way, like so what the partisan function which you can write now, you can write down the partisan function that we started out as this exponential of 2z, where g is in terms of K and H. Uh, 2Z, it will be uh, yeah. So this partition function. Now, if you see, we can write it down as this additional 2z, uh, like when multiplied with this n by 2 number of spins. So uh, for the yeah, so when you have the single particle, not single particle partition, the total partition function if you write. So it is 2z n by 2. The n by 2 because we have reduced the number of spins this time, whereas we have tested out the even ones, and then this times the partition function uh, in this form. Uh, that is, this purely comes from the effective Hamiltonian of the Ising system. So that is, or basically, that is n z k h j is, g is written in terms of k and small h, and this is yeah, some over s, uh, right, an exponential of minus theta h prime. H prime is your new Hamiltonian. So uh, right. So this is how you can you get the recursion relation, and then you find out how this uh, renormalized parameters, which are all the prime coordinates like k prime h prime, all the prime parameters in terms of the original ones. So like probably we can discuss something more about fixed points here. Um, Maybe we do not have enough time also. Maybe we can see if there is like any possibility next time. Like if we find some more time, like even next time we have planned for something, we would like to go over all the topics that has been uh, discussed previously, and some we'll see some crucial problems which could be uh, like vital for your perspective of your test or the examination that you will be attempting soon. And yeah, we'll see some any other questions if you would be having from your side, like if there is any issue in understanding of certain problems or also concepts, we can discuss them. And also we'll see likewise how we have missed out some of the other problems or topics in our previous discussion, like how uh, as we as we are interested in understanding this fixed point analysis also, like from here, like we can also add it to the next time's discussion. And yeah, so right here, like there are no I mean, like these are the recursion relation which are essentially you need when you do a RG transformation. So this is what you get the solutions, and yeah, so this is how you do a RG transformation. So we have done for a simplest case like for the 1D hygiene system. So and likewise, this description will be followed in other places as well, and uh, and yeah, like you can go through and also the assignment problems, like that is what basically we discussed here, and you can, yeah, you can also see if there is any more related problems. Maybe I don't think in the assignment, but it would be there in your uh, discussion lecture videos, or the lecture videos of the instructor. You can see, you can, and also some more topics that has been discussed in this week also. We can also check back if you having any issues or anything that you are struggling to get things cleared. So please let me know. Uh, and yeah, so here I think we are more or less done. So you can, yeah, you can submit the assignment, like when so I think uh, the assignment submission due is still there, so hopefully you are submitting all of your assignments so far before this also, even before week 7, week 8 also, like you have submitted them hopefully quite on time. So uh, and then yeah, that is fine. So uh, okay, so we are done for this session, for our final session, but there is one more additional extra session, so which is coming up soon uh, in a couple of days, or maybe just maybe in 3 days. Let's see. And uh, so like so far as I remember, so it would be on March of 17, I guess. So like you would be getting the reminder as well. So if you have any problem for the one last time, like you can join and you can uh, you can sort it out before you appear for your test, and yeah, that will finally and completely conclude your this NPTEL course for you. And so hopefully you had a nice time in learning this course, and yeah, so hopefully it will somewhere will help you out in the future, and its concepts and lesson will give you some advantage maybe in the future. So yeah, so yeah, that's it. We'll see again for one more time. Yeah, okay, let's end it here. So see you.